Good afternoon, men. What we're going to do today are some calculations on series and parallel capacitors. Before we do that, let's take a look at some quantities that we need to know about. You've seen some of these before, other ones you haven't. It's important to know what the symbols and the units are for each of these quantities. First, let's take a look at one we're familiar with. That would be charge. Symbol for charge is either a lowercase q or an uppercase Q. The units for it are capital C, and that is named after a French scientist by the name of Coulomb. When we write the word Coulomb, we use a lowercase, even though it's named after a person, but we use an uppercase for the unit. The next one is one you hear a lot. You may not fully understand what it is, but we'll get there. That would be voltage. The symbol for voltage is capital V. There's a fancier name for voltage that we'll get into later on, but I don't want to confuse things right now. The units for voltage are also V, capital V in both cases, and it's spelled with lowercase v again, and that's named after a scientist whose name is, or was, an Italian scientist by the name of Volta. He built some early batteries. The next one has to do with capacitors, and that is capacity. This is not quite the same as volume, but it's sort of like it. The symbol for that is capital C, and the units on that will be the farad, capital F. It's spelled lowercase F-A-R-A-D. This is named after a scientist by the name of Faraday. He was a British scientist, and because his name was so long, they just shortened it to Farad instead of Faraday. Okay, so first we're going to find the charge on a single capacitor in a circuit. Then we're going to do two capacitors in parallel, and finally we're going to do two capacitors in series. So let's get started then with our first one. That would be the single capacitor in a circuit. So I'm going to draw a diagram of what we've been doing, the upside down battery, and we're going to use in this format for one more time. So this would be the negative end, this would be the positive end, and we could find the voltage of that battery. What we're saying in these problems is it's the electron that moves, and that is correct. That's what truly happens. Protons don't move. But what scientists and electrical engineers decided quite a while ago was to use what's called conventional current instead of this. What we're doing today, we're saying that the negative charge moves. That's called electron current. It introduces negative signs, which people try to avoid, including me. And that's how we're going to do that. This next problem here. So what do we know about this thing? We know that the voltage of that battery is 6 volts. The capacity of the capacitor is 8 microfarads. Remember, that means 8 times 10 to the negative 6 farads. Sometimes you'll need to use that in calculations, other times you won't. And this is going to be a time when you don't need to use that. So Q equals how many microcoulombs? All right, to do this, we need an equation that we came up the other day using our capacitor analogy, and that was Q equals CV. And in this situation, we already know what C is. That would be 8 microfarads. And we know what V is. That would be 6 volts. We don't have to convert this micro into 10 to the negative 6, because whenever you multiply it by another number, it's still going to come out micro, but in that case, microcoulombs. So that would be 48 microcoulombs. And that would be the charge on that capacitor. So that's all you have to do in a problem like this. Now, what is going on in this problem? I'm going to draw a graph here of the charge versus time. And what's going to happen when we first flip our switch up here, so I just close the switch, what's going to happen is the charge on the plates of the capacitor are going to build up, and then they're going to level off. And what we have up here is an asymptote. And you've seen that before in math. And this value would be Q max. So the asymptote is a value that the charge approaches, but it never gets there. And when you have a graph like this, this is called an exponential. And that's about all you need to know about this problem right now. There's one other thing we could take a look at, but I think we'll save that for the next problem. Okay, so next one we need to work with. It's a little more complicated. And that'll be two capacitors in parallel. So two caps in parallel. We're also going to use what's called conventional current. Conventional current. Why conventional? Often scientists get together in large groups and they discuss what they're going to call various things, what symbols they're going to use, what units they're going to use, and so on. And quite a while ago, they decided to pretend that the thing that moves around the circuit is a positive charge rather than a negative charge. When you do this, it makes a little more sense mathematically. It goes from positive, that would be a higher energy, you could say, to negative, which would be a lower energy. So it seemed to make more sense, and it eliminates difficulties in majority of problems. There are just a few cases where you need to use electron current. We're not going to worry about those because we're not going to do that. Okay, so let's take a look at the circuit we're going to use. When you use conventional current, I'm going to flip the battery over to remind you that we're using conventional current. This would be the positive end of the battery. This would be the negative end of the battery. And we're going to call the voltage of the battery VB to distinguish it from some other voltages in the problem. We're going to take this across this wire. We're going to bring it down here to capacitor number 1. And we're going to bring it back around and connect it with the bottom of the battery, which is the negative terminal. Then over here, we're going to hook it up to capacitor 2, which we'll call C2, and bring the wire around and connect it again. By the way, these two red dots here, those are called nodes. A node is where 3 or more wires meet. And those are important in some of the problems we're going to be doing. I'm going to put something else in that we haven't used, and that is a ground. Since this is a battery circuit, they're usually not hooked up to the ground, but the ground end of the problem is the negative terminal of the battery. And the voltage at ground, VG I'm going to call it, is by definition 0 volts. And VB in this problem is going to be, I'll give it to you right now. So here's a list of the givens in this problem. V battery is equal to 6 volts. V ground, of course, is 0, as we just talked about that. Capacitor number 1, notice I made it a little wider, the plate's a little bigger, just to remind you that it's a little bit larger than the other capacitor. You generally don't do that in a circuit, but we're going to do it when we first start out. This will be 8 microfarads. Remember, the unit for capacity of a capacitor is the farad, in this case a microfarad, because they're small capacitors. What we're going to find is something called C equivalent. And what that means is if I wanted to replace these two capacitors with one, what equivalent single capacitor would I need to get the same results as I do with two? You may wonder, why would you want to do that? Sometimes to simplify the circuit, other times to help you do calculations. In this case, it's going to help us do calculations. Okay, there's more information we need to look for. One of those is going to be V1. I'll explain that in a minute. Another one is V2. Another one is Q1 in microcoulombs. And the final one is Q2, also in microcoulombs. So obviously this is a little more complicated than the first problem we did because it's the capacitors. There are a lot more things that we have to do. Okay, first thing I'm going to do here is I'm going to color these wires up here. The ones that come out of the battery positive terminal, I'm going to color them red. And that's typically the color of wires used in a battery circuit, like in a car. Often the positive terminal is red or has a red connector. The bottom part is black, but that won't show up as well, so I'm going to make it blue. So all of this stuff down here is attached to the negative terminal, and it would be at a voltage of 0. So the red would be 6 volts. The blue would be 0 volts. So every place on that wire, I forgot one of the red ones up here at the top. Whoops, go away. Make sure you also indicate that that one is red. Okay, so that looks nice. And then what we see is the voltage across each cap and across the battery are all 6 volts. There is a device called a voltmeter, and if you put that voltmeter, one wire of it to the red wire in our circuit and the other to the blue wire, both of them that should read 6 volts every time you do that. Okay, let's carry on. We already know 2 of these 3 values here, C1, C2, and C equivalent. So what I'm going to do is make another little drawing here to show you what this would look like if we just did a single capacitor. So it would come out like this. And of course this would be VB, this would be VG equal 0, and this would be C equivalent. Okay, so what happens then when we flip the switch on this circuit? I'm going to make the electrons green for this problem because I'm already using red. So the battery would push out the first electron. That would push all the electrons along this wire down one space, and we would find that when you get to the node here, this point up here where the 3 wires meet, the electron has to make a decision of which way to go. How it makes that decision, nobody really can tell, but let's say it goes onto this plate here. That then pushes an electron off the lower plate, which makes that plate positive, and that electron that goes into that blue wire goes back toward the battery. It pushes all the other charges down one space, and we find a negative goes into the battery here, just as one came out of the battery at the beginning. So this one comes out, pushes, 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 and finally one at the tail end gets pushed back into the battery. Okay, we've done that before. That repeats every time a charge comes out of the battery. I'm going to clean this up a little bit. Okay, so next, the battery pushes out another electron. I'm doing it wrong. Positive charge. We're pretending positive charges are moving. So what's going to happen is each of these is going to be reversed from the way we were doing it before. So a positive charge, which of course can't really move, but we're pretending it can, the positive charge comes around, gets to the node, splits off, in this case, pushes a positive off the bottom plate, leaving the bottom plate negative. That pushes more positives, and it pushes a positive back into the battery. The battery pushes out another charge, positive. Same thing happens. This time it might show up on this plate over here. And it pushes a positive off this plate, making it negative. This process continues over and over again. Every time one comes out of the battery, you pick up a positive on one of these capacitors and a negative on the other plate. Positive, negative, and so on. These will be matched all the time. Every time you put a I said that wrong. The voltage across each of these is the same, but you're not going to get the same number of charges because capacitor 1 is larger than capacitor 2. It's going to end up with more charges on it. The voltage will be the same, but the charge will be larger on the larger capacitor. So what we need to do then is to calculate that. So to find the charge, we use Q equals CV. In this case, we're going to use Q1 equals C1 V1. Well, V1 is equal to 6 volts, so is V2, so we're just going to call it V. C1, if we look at our givens over here, we see that C1 is 12 microfarads. The voltage is 6 volts. And the total charge on capacitor number 1 is 72 microfarads. We'll box that. So that covers that problem. We're going to do the same thing with number 2. So Q2 equals C2V, which would be then 8 microfarads from our given table over here.
Let's begin today with prayer. In the name of the Father, and
So continuing with this problem, we have 8 microfarads times 6 volts because the voltage across each capacitor, as we mentioned earlier, is always in this problem going to be 6. So that would give us 48 microfarads. And because it's smaller, of course, it holds less charge. Now going back up to our equivalent capacitor, we saw over here, I put 3 charges on this capacitor to represent a little bit more, and 2 on here, a little bit less. So let's put all 5 of those now on this capacitor, indicating that the equivalent capacitor has the same total charge as these 2 capacitors independently. So instead of a charge coming to the node, some of them going here, more of them, and fewer of them going over here, they don't have a choice if we replace it with a single capacitor that is identical in properties to those. It ends up with the same amount of charge as the 2 individuals would have. So we can then just say that Q equivalent is going to be equal to Q1 plus Q2. And of course that's going to be 72 microfarads plus 48 microfarads. So Q equivalent then is going to be 120 microfarads. Whoops, I've been making a mistake. We're doing charge here, so this is microcoulombs. And I have to go back and fix that error up here. Remember, when you make a mistake, you have to locate it and you have to fix it. So we'll do that right now. Okay, so there we go. So that's Q equivalent. And if you replace those 2 with a single capacitor, it would have this much charge on it. So let's take a look at our table and see if we've filled in everything. What we found was, what we knew was V1 and V2 and VB are all going to be 6 volts. we just calculated here Q1, calculated here Q2, and I left one off the table. Q equivalent equals how many microcoulombs? We calculated that over here. So we've done everything we've needed to do except for one, and that is, what is the value of that equivalent capacitor? Is it 20? Is it the sum of them? Is it the difference? Do you divide one by the other? All good questions. So let's see what we need to do. How would you go about finding that? Well, we have an equation that says Q equals CV, and we're looking for the capacity of the equivalent capacitor. So that would be this thing up here. So we're going to label this C equivalent. We don't need to call it V equivalent because all of the V across every one of these capacitors is going to be 6 volts. But we do need to call this Q equivalent. So our working equation then is going to be V equals Q. Oh, no, I'm not solving for V. I'm solving for C equivalent. So C equivalent is going to be equal to Q equivalent over V. So what we're doing here is we're taking this amount of charge, which the equivalent capacitor we determined would hold, divided by the voltage across that equivalent capacitor, and that will give us the capacity of the equivalent capacitor. So what is Q equivalent? Right here it says 120 microcoulombs, 120 microcoulombs, and the voltage would be 6 volts. So C equivalent comes out to be 20 microfarads. Okay, so that should not be a big surprise, because if we take a look at what we had earlier, we had 2 capacitors side by side like this, and what we essentially did was slid them together like so. So this would be one, this would be the other, and we run these wires up here like this. So we push them together until they're touching, and for all practical purposes now we have one big capacitor, and you don't really need 2 wires here. All you need is 1 wire. So we now have a larger capacitor, and obviously it has a larger capacity, and it holds a larger charge, and everything seems to make sense. If you have any questions on this, now would be a good time to make a note of that. Just write that in your notes, and when I get back on Thursday, we'll go over that. All right, we like to come up with conclusions on problems like this. So let's write an equation that tells us how we can add capacitors in parallel. So adding capacitors in parallel. And remember, we call them parallel because the paths of the positive charges as they go onto the capacitor are parallel to each other. Okay, so in this problem we said C equivalent equaled C1 plus C2. We can expand that plus C3 and so on, and usually you don't want to sit there and write every single one of them down. So often in physics and math they just say dot, dot, dot. Or if you're into summation notation, you could say C equivalent equals the sum of I equals 1 to n of C sub I. What does that mean? You start with I equal to 1, and you write down C1. Then you kick up I to 2. So then you add on C2, and so on. N would be the maximum number. In our problem, n was equal to 2, so we just had C1 plus C2. If it were equal to 100, you'd have C1 plus C2 all the way out to C100. Generally, you don't have something that large, but that's how you would write it. Okay, that pretty much wraps it up for everything that we want to do with capacitors in parallel. Now we're going to move on to capacitors in series. What does it mean to add capacitors in series? Well, let's start with our battery. We're going to use conventional current again, so this will be the positive end of the battery, this will be the negative end, and we're going to pretend that the charges move from positive to negative, so they're going to go clockwise around our circuit. So VB would be voltage of the battery. So we're going to bring this around, and we're going to attach it to capacitor 1. And then we're going to put them in series, so it means one after the other. They're going to be in line rather than next to each other. Kind of like a TV series, first you see one show, then you see the next one, and so on. You don't watch them all at once. So this would be C2. We're just going to limit ourselves to 2 here. We bring this back around, attach it to the negative end of the battery, and we'll put in a ground symbol, meaning the bottom of the battery, VG is equal to 0. Okay, that's nice. What are we going to know about this problem? The first thing, we need to put some givens on this problem. So let's put them over here. V battery is going to be 6 volts. V ground, of course, is going to be 0 volts. I'm going to use the same 2 capacitors, but we're going to get different results. C1 is going to be 12 microfarads. C2 is going to be 8 microfarads. And we're looking for C equivalent. This is going to be a little harder than the last time, but we do it every year, and pretty much everybody figures it out, so it's not a big deal in the long run. We're going to, whoops, where'd that come from? We're going to, my pen's going crazy here, in a minute. Okay, Q1 is going to be unknown. Q2 is going to be unknown. And Q equivalent is going to be unknown. So there are a lot of things we're going to have to do here in this problem. And let's get started with that. I'm going to do the same thing I did before. I'm going to color all of the positive 6-volt wire red. I have to stop there because we don't know that little short piece of wire here, we don't know that that's going to be at 6 volts. In fact, if you think about it, it probably isn't going to be at 6 volts. Since it's halfway around the circuit, would it be 3? Sometimes, if these two are equal, it would be 3. But they're not equal. Therefore, we can't say what it is right now. We'll get to that later. Now let's color all these 0 voltage wire blue. And that's that. Because we don't know what's going on in the middle, I'm going to color this middle wire here green. You might think, oh, I could probably figure out what the voltage is at that green, on that green wire by playing around with ratios or playing around with numbers. You might be able to figure that out, but that's not physics. Physics requires equations, not just playing around with numbers and doing what seems like it will give you the right answer. You need to be able to write an equation for it. The other problem is if you have 3 or 4 capacitors in series, it's going to be a lot harder to do it just playing around with numbers. If you have the equation, they're all easy. Okay, so the same thing we had before. We know that when we push a charge, a positive charge in this case, because we're using conventional current, and that means that we pretend the positive charge moves. The battery pushes out a positive charge. We get a positive charge here. What does that positive charge do? Its electric field pushes a positive charge off the plate and leaves the bottom of this plate negative. So we have a positive one shows up here. Its field pushes a positive off this plate into the green wire, leaving the bottom plate negative. That charge that went into the green wire pushes the charge, positive charge, out of the green wire onto the plate, making the plate positive right here. That positive going into the plate, it creates a positive electric field. That positive electric field pushes a positive off the bottom plate, leaving the bottom plate negative. That then pushes on all of these, and the very last positive charge over here at the bottom is pushed up into the battery. So we have positive coming out up here, pushing all of these in line, and even pushing across the gap in the wire, which capacitors can do, and pushing around here. So this charge that went into here, it's not the one that left the battery, it's just the first one in line right below the battery. Kind of like a bucket brigade. You add one bucket to the end, one comes up off at the other end. Another thing to remember, that when we had the other parallel circuit, we didn't necessarily have the same number of charges on each capacitor, because at the node, when the charge got to that, either go straight ahead or make a right turn, when the charge got there, let me go back to the picture, when the charge got here, it had a choice: go right into this capacitor, or go straight ahead and go onto the C2 capacitor. More of them will go onto here because it's bigger, fewer on here because it's smaller. Now we're in a situation where there is no choice. Every charge that comes through here has to push things along this one path only. Remember, the charge doesn't go through the capacitor. It influences the charges on the other plate to move away. So you will always get 1 for 1. So the charges here are 1 for 1. And what I mean by that is, if one capacitor gets a positive charge, the other one gets a positive charge. If there are 3 in a row, all 3 of them will get 1 positive charge. If you put 2 charges on, which I'll do now, so another charge comes out, eventually pushes a positive onto the plate, which pushes a positive off the plate right here. That positive goes into the green wire, which pushes a positive onto the plate right here. That positive has a positive electric field, which pushes a positive off the plate, making the plate look positive. That positive goes into the wire, pushes all of these in line, and the last one in line to go off gets pushed up into the battery. I forgot to put one up here at the beginning, so this represents 2 charges coming out, 2 charges showing up on the capacitor, not the same charges, 2 charges showing up here, also not the same charges, and 2 charges coming out here going back into the battery, again, not the same charges. Okay, so this is going to make things a little simpler in some ways and a little more complicated in other ways. What we can say from this is, if we replaced those 2 capacitors with 1, and we called that C equivalent, how many charges would it have? Well, since only 2 came onto the capacitor, there would only be 2 on the equivalent capacitor. These 2 charges here are not different they're different charges, but they're not new charges. These 2 show up because these 2 pushed other ones there. It's a little confusing to see that we don't have 4 charges here. We just have the 2 that went onto here, pushed 2 onto here. And so if we replace it with an equivalent capacitor, we say that there are just 2 charges on that equivalent capacitor. Because when you look at the top of it, that's what you see at the top. And when you look at the bottom of it, you see that. So if we put this inside of a box, like so, and all you could see was, let me change the color here, and all you could see was the top of the capacitor inside that box, you would see 2 positives here, and you would see 2 negatives here. So that equivalent capacitor hiding in that box is exactly the same, behaves exactly the same as if we just put 1 equivalent capacitor in that box. Looking through there, we would see 2 positives on the top and we'd see 2 negatives on the bottom. That made sense? Good. If not, don't worry about it. Okay. So I'm going to knock this out of here so we have a little bit more room. All right, what are we going to do next? We can say that the Q equivalent capacitor is going to have the same charge on it as capacitor number 1, which is also the same as the charge on capacitor 2. So it's going to be 2, 2 up here, and 2 on the equivalent capacitor. That's nice. So now we have another problem, though. We have the problem of what are we going to do with that green wire in there? What are we going to call the voltage there? Unfortunately, it looks like we're probably about out of time here. I'm going to continue this video. I'm going to put a pause in here. I'll just write that, pause. And I'm going to stop it. And if you're ready to be dismissed from class, then you can take off, and we'll see you on Thursday. I'm going to continue the video, however. So if you want to look at the rest of it on YouTube tonight, it'll be there. It's a little more complicated. It might be a really smart idea to take a look at that, because this is a little more complicated than the last problem, and I do expect you'll be able to do this in the future. So you might as well get a start on it now. Okay, here we are. I'm assuming that you might be at home, and as a great student, of course, you're going to be looking at this ahead of time to see what is coming. Okay. In these problems, we've seen a situation where we have a capacitor, and we had a different voltage on the top than on the bottom. So, for example, on one we had 6 volts up here, we had 0 volts here. In this double capacitor problem, we have the following, and I colored in the top wire red, I colored the bottom blue, and I colored the middle one green. So we know that across here it's going to be 6 volts, but we don't know what it is from here to here and from here to here. But what we do know is that we could call this difference V1, and we could call this difference V2, and we could call this difference here V equivalent. So I'm going to write an equation. It says the same thing that I just drew there. The voltage across that whole set of capacitors, the equivalent voltage, let's say, across the equivalent capacitor, is equal to the voltage across number 1 plus the voltage across number 2. So what are we going to do with that? Well, we have an equation that says Q equals CV. And if we could replace these V's here with the Q and the C, we could possibly end up with a useful equation. So we know that V equals Q over C. So on the left side here, what we're going to have, to get this out of here, what we're going to have there is V, whoops, that's not what I want. V equivalent is going to be Q equivalent over C equivalent, and that's going to be Q1 over C1 plus Q2 over C2. But what we said earlier, way back up here, was that all of those charges are the same. So we should give them a single name rather than have 3 different names. I'm just going to knock off all the subscripts and write it as Q over C equivalent equals Q1, and not Q1, Q over C1 plus Q over C2. Now, it's obvious that there's a Q in every term, so we could multiply the whole thing by 1 over Q, or divide the whole thing by Q, And what we're going to end up with is 1 over C equivalent equals 1 over C1 plus 1 over C2. That's the equation we're looking for. It's a little tricky to do it by hand, so generally what you do is you do this in your calculator like so. You would write it as 1 over C equivalent, and then capacitor 1 was 12 microfarads, and capacitor 2 was 8 microfarads. And then on your calculator, you punch in the following: 1 divided by 12 plus 1 divided by 8 equals, no parentheses needed here. And after you hit the equal sign, we need to take the reciprocal. Again, there's no need to write anything down or store any numbers. You just type in on your calculator the key that says x to the negative 1, which is the reciprocal key. And if you do that correctly, what you're going to get here is that C equivalent is equal to 4.8 microfarads. So that's the equivalent capacitance. I call this reciprocal addition because what we're doing is we're adding reciprocals and we're taking the reciprocal of that addition of reciprocals. It gives you the right answer. What if you have 3? You add a third term. What if you have 4? So on, add a fourth term. All you have to do is keep saying 1 divided by C plus 1 divided by C plus 1 divided by C equals C equivalent. Okay, so we've got that. And notice that C1 was 12 microfarads and C2 was 8 microfarads. The equivalent capacitor must always be smaller than that. We'll discuss that someday in class in the near future. But what we need to do now is finish this problem. There's only a few more minutes, so let's take a shot at that. Okay, so we know what C equivalent is. C equivalent is equal to 4.8 microfarads. And what would Q equivalent be? That was one of our unknowns. So Q equivalent equals what? Let's see, let me go back if I can find the beginning of this problem. Okay, right here, we wanted Q equivalent. So let's go find Q equivalent. Q equivalent, by the generic equation, Q equals CV. Oh, my pen's dying again. Q equals CV. The C is going to be C equivalent. The V is going to be the voltage across that equivalent capacitor, which is just 6 volts. So it's across the whole thing, not across an individual one. So we plug in here for C equivalent 4.8 microfarads times 6 volts. And we find out that Q equivalent ends up as 28.8 microcoulombs, not microfarads, but microcoulombs. So that's Q equivalent. What's Q1? Because we said these charges are 1 for 1. Every time one capacitor gets a charge, all the other ones in the line get 1 charge. So Q1 is going to be identical because we said back here somewhere, right here, we said back there that all the charges are equal. So we just say 28.8 microcoulombs, and Q2 equals 28.8 microcoulombs, and we're finished with that part. The last thing we need to do is to solve for V1 and V2. We don't know what those are. We go back to our unknown list. I didn't put it there. I should have. So V1 equals blank volts. V2 equals blank volts. We're looking for those 2 values. We're going to find out what the voltage is on the green wire, of course, in doing that. Okay, so how do we solve for that? Well, we know with the equation Q equals CV. If we want to solve for V1, we need to put 1s on all of these. So that would say voltage 1 equals Q1 over C1. Q1 we just figured was 28.8 microcoulombs, and C1 is equal to 12 microfarads. So V1 is going to equal to 2.4 volts. Okay, so that's nice. What that means is the top of the capacitor is at 6 volts. The bottom of it is 2.4, smaller than that. Let's calculate Q2 or V2. So Q2 equals C2 V2. V2 equals Q2 over C2. Q2, all the Q's in this problem are 28.8 microcoulombs. But now we're over 8 microfarads. So V2, when you work this out, comes out to be 3.6 volts. So we've got everything we were looking for. Let's take a look again and see what this means. We're going to figure out what is the voltage at each of these red dots here. If we start on the top, this voltage here is going to be 6 volts. If we go to the bottom, we know this one here is 0 volts. And if the voltage across V2 is 3.6, then this voltage here is going to be 3.6 volts. The voltage drop across here is 2.4, and the voltage drop across here is 3.6 volts. There's a rule here. When you're in series, the larger cap has smaller voltage drop. And of course, the smaller cap has a larger voltage drop. So as you can see, this is the smaller cap at 8 microfarad, its voltage drop is bigger. This is the bigger one, voltage drop is smaller. Okay, so that's about everything I wanted to do with this. One last thing, let's just do this. V battery is equal to V1 plus V2. V1, that would be the drop across number 1, would be 2.4 volts, plus the voltage drop across number 2, which would be 3.6 volts. So V battery should agree with this. 6.0 volts is the drop across the battery, or is the voltage across the battery. It's also the voltage drop across these two capacitors in series. Okay, that's it. We'll finish this up on Thursday.